This is Mrs. Palmer-Quay with the third video for Module 8. In this video, I'm going to talk about covalent bonds, which are the kind of bonds found in covalent compounds. Let's start with a little bit of review. Remember that chemical reactivity, or how elements react with each other, is determined by the valence electrons, those electrons in the outermost energy level of the element. And elements react together to form compounds so that each atom will have access to 8 valence electrons. We call that the octet rule. Ionic bonds, which were covered in a previous video, form when electrons actually move from one element and deposit themselves on the other. These occur when there are large differences in electronegativity between the elements in the compound. And as a result, because electrons move, we form ions, or atoms that have a positive or negative charge. And that is this charge that actually holds the compounds together by electromagnetic force. Positive and negative charges are attracted to each other, and that's what holds the compounds together. The chemical formulas for ionic compounds really are empirical formulas because they form lattice crystals with many positive and negative ions surrounding each other until you've run out of ions to make the compound. So now we're going to talk about covalent bonds. Well, covalent molecules, if you remember, are formed by two nonmetals, two or more nonmetals. And in a covalent bond, the electrons are shared. They don't move from one atom to the other, but they are shared between atoms. There's actually a balance of attractive and repulsive forces, and covalent bonds form when there are small differences in electronegativity. You can think of these electrons as being shared or even being fought over. One atom says, I want this electron, and the other atom says, no, I want it, and they're both close enough in strength that they can kind of pull at it back and forth. But as a result, as in ionic bonds, a covalent bond allows each atom to have access to 8 electrons, following that octet rule again. We call these shared electrons either shared pairs or bonding pairs or bonded pairs, as compared to lone pairs, pairs of electrons that are not shared. And I think this will become more obvious as we do some Lewis diagrams. With covalent molecules, the chemical formulas do represent the molecular formula. Because these are more self-contained molecules, they don't form a crystal lattice the way ionic compounds do. Let's start with thinking about water. First of all, what are the valence electrons for the two elements involved in water? Well, hydrogen is our very first element, so we know it only has one valence electron. So we can just draw hydrogen here with its one valence electron. Well, oxygen is not as, it's close to the periodic table, but it's not right at the top. And so it has energy, it has 2 energy levels, and in its second energy level, we have 2s2 electrons and 2p4 electrons. This is for oxygen. So when we're drawing our valence electrons with the Lewis dot structure, we're drawing the ones in the second energy level because the ones in 1s2 don't count. We're always looking at the highest energy level. And so we've got our 2s2 electrons, and then we have our 4 2p electrons. And so the Lewis dot structure for oxygen looks something like this. And as I said in the previous video, you really don't have to be too particular about how you put those dots around as long as you have 2 paired electrons and then 2 lone electrons. So how can we combine hydrogen, 2 hydrogens, with oxygen so that all of the electrons or all of the atoms have access to the number of electrons they want to stay stable? Now hydrogen, as I said earlier, is sort of our exception to the rule. It wants 2 valence electrons, not 4. But the oxygen wants 8. So this one wants 8 valence electrons, and hydrogen wants 2. So if you picture, if you kind of rearrange things, we take our oxygen here, we'll leave our 2 lone pairs over there, here's our oxygen, and we're going to bond it to hydrogen. I'm going to do hydrogen in a different color with its 1 electron here and here. And if you see in this model, then each hydrogen has access to the 2 valence electrons that will make it happy, to anthropomorphize it, and each oxygen will have access to 8 valence electrons. And so this makes water a stable compound with covalent bonds here between the oxygen and the hydrogen and here. These other electrons, as I said, we call them lone pairs. They're not bonded to anything else. How about another example? Ammonia. Well, again, we've got our hydrogen with its one valence electron, and we have 3 of those in this molecule. And then we have nitrogen. What's the electron configuration for nitrogen? Well, it's actually element number 7. It's 1 back from oxygen, so it has that 1s2 that we don't need to think about. And then we've got 2s2 and 2p3. So we have 5 valence electrons around our nitrogen. So 1, 2, 3, 4, and 5. So you see we've got 1 lone pair here, but we have 3 places where we can make another bond. And so in each of those places, that's where we slide in our hydrogens. So just to redraw that again over here, putting our nitrogen with its lone pair of electrons on one side and the ones that we're wanting to bond on the other 3 sides, and we slide in our hydrogens. And just as we saw with water, then each of the elements in this molecule, each hydrogen has access to 2 electrons here, sharing it with the nitrogen, and the nitrogen has access to 8 electrons. So we have a stable ammonia molecule. Carbon, again we're working with hydrogen, but carbon, if you look at carbon, well, it's 6. We're kind of going backwards on the periodic table, so we've got that 1s2 that we don't need to worry about. 2s2, 2p2, so we've got 4 valence electrons in carbon. So carbon, we can just put all points of the compass here, and I think you can just picture now we're just going to put a hydrogen at each of those places, and so that when we're done, just like we've seen on all the other examples, each hydrogen now has access to its 2 valence electrons, and it's in a stable form, and the carbon has access to 8 electrons. So it doesn't matter that 1 electron is coming from one element and 1 from the other in each of these bonds. What matters is that carbon has the ability to access the 8 electrons, an octet of electrons, and that makes a stable compound. Now, when there is 1 pair of electrons being shared between 2 atoms, that is known as a single bond, and we can also show that as just a line. So you will also see these structural formulas drawn like this with a line instead of doing the full Lewis dot structure. Makes it a little bit tidier to do it with a line. Well, there are more than single bonds possible with covalent bonds. We also have double bonds, and this familiar carbon dioxide molecule is an example. If you think about how the Lewis dot structure goes, you've got carbon over here with its 4 valence electrons, and then you have oxygens that have, again, 6 valence electrons, 2 paired already, but 2 that are looking for a pair. And there are 2 of them. So if I just draw them this way, putting the already paired electrons to the outside and leaving our unpaired ones on the inside, you can see that we could pair these 2 together, and these 2 together, and these 2, and these 2. And as a result, oxygen has access, to 8 electrons, and this oxygen has access to 8 electrons, and this carbon, I'm getting kind of messy here, but this carbon has access to 8 electrons. So they all fulfill the octet rule, and we end up with, again, using this lines for bonds, we have these double bonds instead of a single bond holding the oxygen and the carbon together. So we have not only single bonds, but we also have double bonds. And the double bonds sort of tighten up this molecule, pull it together a little bit more strongly than if it was just a single bond. Another molecule with double bonds is this dicarbon tetrahydride, more commonly known as ethene. And the double bond in this case is found between the carbons. So we've got our carbon molecules with their 4 valence electrons, and then, of course, our hydrogen molecules. So with our hydrogen, we've got 4 hydrogen. Whoops, I missed one in here. This carbon needs another one. We've got 4 hydrogen positioned around the outside. And this structure, you might want to adjust things to make them more on a little bit more of an angle here. But you can see that then we have the 2 carbons here can share an electrons, and these 2 electrons can be shared. So again, each carbon will have access to 8 electrons, each hydrogen will have access to 2. And we more commonly will show this particular molecule this way, so that we're showing all of our bonds as lines. It's a little bit less messy than trying to draw dots. And we can go one more level. There are triple bonds that exist in covalent compounds. Nitrogen gas, one of those homonuclear diatomics. If you remember, nitrogen had 5 valence electrons. And so I'm sure you can picture how each one of these individual lone electrons, can pair up. When you put 2 nitrogen molecules together, they will form 3 bonds in the center, leaving the lone pairs here on the outside. And again, another triple bond, acetylene or ethyne. You've got, again, a carbon triple bonded in the middle, and then a hydrogen on each side. So hopefully by now you can kind of picture what's going on without doing all of the Lewis dot structures. Lewis dots are sort of get you started thinking about it, but hopefully you can then make the jump to what these would look like. That each one of these lines represents a shared electron, one from one element and one from the other. Your book doesn't mention it, but there's another type of covalent bond called a coordinate covalent bond, where one atom will provide both electrons for the shared pair in order to fulfill the octet rule. And carbon monoxide is an example of that. If you think about, we've got our carbon, and it has our 4 valence electrons here, and oxygen, which has 6 valence electrons. We can see how these 2 would very easily form a bond, and these 2 could form a bond. And what happens is that this set of paired electrons from the oxygen goes in to make another triple bond, and these 2 electrons just hang out as a lone pair on the carbon, so that its form would look like this, with a lone pair of electrons for each atom on the far side. So that the book doesn't mention this, but I just thought I'd let you know. There are also exceptions to the octet rule that we're not going to talk about in this class. Everything you will be asked to do for tests will have electrons that will nicely fulfill the octet rule. And finally, just a word about bond strength. We determine bond strength by how much energy is needed to break the bond, to separate the atoms in a bond, in a molecule or a compound. And so covalent bonds in general are stronger than ionic bonds because the electrons are being shared and they're sort of a tighter molecule between the elements. And the multiple covalent bonds, double and triple bonds, are stronger than the single covalent bonds. This will become more obvious as we work next semester dealing with bond energies, but I thought I would just throw that in now to kind of get you ready for the subject. So that covers what I want to say about covalent bonding. Hopefully you can see the difference between covalent and ionic bonds and have some idea how to create these compounds using Lewis dot structures.